So we've looked at speed and acceleration, and this is a section where we get into some information that I really want to make sure you understand. It's kind of the nitty gritty of all of the physics concepts come back to force. So we're going to look at forces. We're going to look at Newton's laws. It's going to be more definition based, just a little bit of calculation, and then you'll have a short quiz to do on SAM. So what is a force? A force is any push or pull. We're going to find as we go through Newton's laws that force is directly proportional to the mass of an object. Therefore, the heavier an object is, the more force that's required to push or to pull it. The unit for force is a Newton. It's force, the laws of forces were discovered by a scientist, Isaac Newton, and therefore the unit was named after him. It's equal to a kilogram times meters per second squared. You'll see where those units come from shortly. Another term that you're going to need to know as we look at force is we're going to need to know mass. And mass is the amount of matter an object is made up of. Now, mass is constant through the universe, so my size doesn't change as I move through the universe, but my weight could change. So mass and weight are a little bit different. We'll talk about that a little further. It's not something you really need to worry about a whole lot, but in the concept of physics, mass and weight actually are two different topics, two different concepts. They're related, but they're different. Now, the SI unit, or the unit we're going to use, the standard unit for mass is always going to be a kilogram. So everything else goes to base units like meters and seconds, but mass is always given in kilograms. And that kind of makes sense based on the size of objects. If you imagine if we measured everything in grams, I mean, if you're talking about the mass of a vehicle, it's going to be a crazy number of grams. So kilograms makes much more sense for us to work with. It's kind of the middle of the common masses that we use, especially in physics terms. Now, things are, we even use it with chemistry, believe it or not. That's why I come from a chemistry background. So when we did physical chemistry, we would look at the mass of particles, and we would use scientific notation in order to list them in kilograms. But often when we talked about them, we talk about micrograms and grams. So one of those things that for you, you will always use kilograms. So in terms of Newton's law, so Newton had three laws. His first law states that an object in motion will stay in motion and an object at rest will stay at rest unless acted upon by an external force. So if an object's moving, its motion won't change. It will continue to move the way it had before unless another force hits it. Likewise, if an object's not moving, it will keep not moving unless it's acted upon by another force. So if we take this little GIF here, I stole at the bottom, and I'm not sure if it's obnoxious that it just keeps playing over and over. But the guy on a bike comes, you notice the bike hits the brick wall, but the person does not. The person is free to fly off the bike. According to Newton's law, because he was in motion when the bike hit the wall, the bike stops, but the person keeps on moving. That's an example of Newton's first law. So a force on the bike stops the bike, but because there's not a force on the person continues to move, flies through the air and lands on the other side. It's one of the things that makes motorcycles a more dangerous vehicle, but it's also the whole principle behind how collisions work. If we're thinking about driving. And a blustery, wintry day like today, driving conditions are one of those things that I think about even though I'm home. I've got a nephew out at work today, and I don't think I'd want to be driving if it was me. So Newton's first law is also known as the law of inertia. So I'll give you the definition of inertia. We're not really going to use this word inertia very often, but I think it helps us kind of understand how Newton's laws apply to everyday scenarios and maybe even scenarios in your trade. So inertia is a property of matter that resists change in motion, okay? So it's because an object has inertia that an object will want to keep whatever motion it has. So a heavier object will want to stay put. I say want as if it has a choice, but will resist change in motion more than a light object. So I'm currently sitting on a wheeled chair. If I push back, this chair will want to continue to roll back until friction from the wheels slow it down due to the law of inertia. By pushing back, I've given the chair inertia, my mass and the speed of the chair want to keep it going at that same speed. So that's Newton's first law. Now there's some practical examples of that, and we'll see that in a minute. So Newton's first law in terms of math speak, because we're going to do some math with this, says that if the overall force or the net force, so the sum of forces on an object equals 0, then an object is moving at a constant velocity or it's at rest. So if the sum of the forces, if all the forces are balanced on an object, it's not changing its speed, it's not changing its velocity, so it's not accelerating, it's at rest, or it's just moving at a constant speed. Situations with balanced forces are very good for us because it often means we're putting less strain on equipment. We typically want things to get up to a speed and then maintain that speed. We don't accelerate for forever. That's not logical. I mean, imagine vehicles. If you just kept accelerating as you drove, that's not logical. You want to speed up and then you maintain a constant speed. So we're going to look at just a couple examples, and this is more thinking examples rather than math examples. Imagine a book sitting on a table. There's a force of gravity pulling down on the book, but there's also a normal force pushing up on the book. So I'm going to draw the forces. It's one of those things that's going to be really helpful for us to do. So we have gravity pulls down. We'll look at the symbols we would use for that, but the table pushes up. If they are balanced, so that means the table can push up with the same amount of force as the books can push down. If the table couldn't, it would collapse. But if the forces are balanced, we're going to get no motion. Okay, so very, very simple. Newton's law says if forces are balanced, if the overall force is 0, an object won't move or its motion won't change. Okay, so that means if it's already moving, it's not going to change speed. So Newton's law in action. I don't know if any of you have done this. This is last year. I'm sure there was a few people in the class that, oh yeah, I've done this. So the head of a hammer can be tightened onto a wooden handle by banging the bottom of a handle against a hard surface. So you take your hammer and you bang it down on a hard surface. So you got a head that's a little loose. You bang it down a couple times and it'll usually tighten up. I remember watching my dad do it as a kid, and it's one of those things I picked up from him. I never really thought about it being Newton's first law. But what happens as you take the hammer and you bring the bottom of the hammer down, the handle stops moving because it's hit a surface. But the head that's a little bit loose, it, according to the law of inertia, it wants to keep going. Just like the little guy on the bike wanted to keep going and fly off. The head of the hammer keeps going down a little bit and it tightens up because the handle gets larger as you move down the handle. Okay, so that's a really simple practical example of where Newton's first law is used and something you might have seen before. Another really good example, I'm pretty sure all of you have probably experienced this. If you haven't experienced it, I'll be surprised, especially when you have winter driving and a little bit of drifting. Not saying you should drift, just making the prediction that many of you do drift. While sitting in the back seat of a car, it makes a hard right turn. You slide across the seat. So you know you're in the car, you're driving along, and all of a sudden you make a quick turn, and especially if you have leather seats or a bench seat, you slide across the seat. Why? Well, Newton's first law says you want to keep moving in the direction you originally were going in. So if we draw a little picture here, so the car is driving along, it makes a right turn. The car was driving this way, your body wants to keep moving forward. So as the car turns, you slide across the seat. It's one of the reasons why in racing vehicles, they use bucket seats that have curves in them. That's to keep you from sliding. Otherwise, it could be rather dangerous. So some practical examples of Newton's first law. Why does the back end of your car, especially on some snowy weather, I don't know when you're watching this, but it's currently Tuesday, March 2nd, and we've got some good stormy weather and, from the best of my knowledge, some icy roads. So as you're driving along the road, you hit, especially if you have front wheel drive, hit your brake, the back end of your vehicle wants to keep on going. The front wants to stop, and that swings you around. I mean, you can do it pretty well in any vehicle and it's a feeling I hate. So I don't do drifting. My husband likes to do it just to get me going. It's my least favorite feeling in the world, because when he drifts around the corner, that our house is right on a corner, if he drifts around the corner coming home or leaving home, it very much reminds me of an accident I had. I wasn't hurt, the vehicle wasn't hurt, but it's a feeling that spinning out of control on the road at 110 kilometers an hour on the highway is not a feeling that I like to repeat or remember. But that's Newton's first law. Newton's second law, it's related. So Newton's second law says, okay, first law deals with if the forces are balanced, there's no change in motion. What happens if they're not balanced? That's Newton's second law. So Newton's second law says, if there's unbalanced forces, you're going to get acceleration. And that acceleration is equal to mass times, it is proportional to the mass. So it's equal to mass times the acceleration. Okay. So if you have unbalanced force, it will be equal to the mass of the object times the acceleration that it has. So net force, it just means the overall force. So you take all the forces that are on an object and you cancel the ones that are in opposite directions, you add them together. So acceleration is caused by all the forces acting on an object. So if you think of an object falling, gravity pulls it down to the ground, there's one force, but you have things like air resistance pushing it back up, slowing it down a little bit. So we know objects don't really fall as fast as gravity can pull them because of things like air resistance. You also know, and I'm guessing you've probably talked about fluid flow in pipes. We're going to talk about some of that. But if there's a corner, anywhere where you can get tight corners, you usually don't want to have really sharp corners because you get drag. So you do gentle corners to avoid friction losses. And that's reducing the forces that are on an object so that the air doesn't slow down. So acceleration can be speeding up or it could be considered slowing down. So depending on the direction of force. So unbalanced forces cause a change in motion. Means there's going to be acceleration. Something's going to speed up or something's going to slow down. And it depends on the sum of the forces. So if I drop a book from 2 meters and there's only a downward gravitational force, so I'm ignoring air resistance. Now that the forces are unbalanced, what does the book do? Well, gravity pulls it down. Nothing is balancing it back up. So it accelerates to the floor. It was at rest when it sat on the shelf. Now that it's fallen, and accelerates to the floor because of unbalanced forces. Nothing we haven't seen there. So let's put Newton's law into action and do some calculations with it. So according to Newton's second law, force equals mass times acceleration. The fundamental principle of force. If a 5 kg block is pushed to the right along a frictionless track, so we're ignoring friction, we're keeping it easy, with a force of 10 newtons, what is its acceleration? So I'll often do a little sketch. So here's my block. We call these sketches free body diagrams. Okay, so you just draw a block to represent the object. It doesn't matter if it's a box or a car or whatever. I like to put the mass of the object in it. It helps me keep track of information. And it's pushed to the right with 10 newtons. What direction will it accelerate? Well, acceleration is going to be in the same direction as the overall force. So the acceleration is going to be to the right. Now we want to calculate the acceleration. So force equals mass times acceleration, and we substitute in 10 equals 5 times A, divide by 5, 2 meters per second squared. Same units as we had in our last lesson, that's acceleration, is equal to the acceleration, and it will be a rightward acceleration. Okay? Or we could say a positive acceleration. Easy, easy question to do. The next one, we have a 650 kilogram car. It's accelerating at 3 meters per second squared south. What's the net force? So force equals mass times acceleration. And we know the mass, so it's 650. We know the net we know the acceleration, so 3.0. What is the force? So 650 times 3. Helps if I pull my notes where I've written my solutions down. $650 times 3 equals 1950 newtons. Force is measured in newtons. So that's the overall force acting on it. Another question, and this one's going to be more important to draw a diagram because there's going to be more than one force on an object. Stan and Kyle are pushing a 75 kg box along a frictionless surface. We're going to make it simple. So this box is 75 kgs. Okay. Stan pushes with 55 newtons and Kyle pushes in the same direction with 45 newtons. As long as they both go in the same direction, we're good. So we have 45 newtons and we have 55 newtons. What's the acceleration of the box? Well, the first thing we need to figure out is how much force is on this box. So the net force is 45 plus 55, which leaves us with 100 newtons. To find the acceleration, then we use our formula. Force equals mass times acceleration. So these forces work together, so they add together. We're going to find in the next example, they work against each other, so they're going to subtract. So net force is 100, mass is 75 times acceleration. Just simple rearranging. Acceleration of this box is going to be 1.33 meters per second squared. So it's speeding up. Okay. The next question has a tricky piece in it, and it's this. Some of you will be familiar with that. We call that scientific notation. I'm going to give you the conversion for it before we get into it. I meant to go through and change. Scientific notation, what this means is 8.50 times 10 to the power of 3 is like multiplying by 1,000, which means this is 8500. Just this 3 moves the decimal 3 places to the right. If it was a -3, we'd actually divide by 1,000. You won't see that very much, but it's in there and I didn't change it, so we're going to leave it be. So that's how many newtons. All right. A vehicle has an engine that exerts a force of 8,500 newtons, while friction pulls back with a force of 1,500 newtons. If it has a mass of 1,250 kilograms, what's its acceleration? So draw our sketch. So there's our box. The engine's putting a force in one direction. And in the other direction, we have this friction force. It's working against it. How much force is there overall on this object? Well, the force, the net force, the overall force, just is the difference between the two. 8,500 minus 1,500 gives us a net force equal to 7,000. Now, in order to find the acceleration, we just use F equals ma. So 7,000 equals 1,250 times A, divide by 1,250. Make sure your unit was in kilograms, which in this case it was. And acceleration is equal to 7,000 divided by 1,250, 5.6 meters per second squared. So it's not complicated math. It's really, you do some math, you add or subtract your forces to find the overall force. And then we're usually dividing by mass or maybe dividing by acceleration in order to find what's the mass or what's the acceleration of the object. Now, the force due to gravity is an example of Newton's second law. Gravity causes an acceleration on Earth, and this is just on Earth, equal to 9.81 meters per second squared. We put this negative in because it's a downward acceleration, although when you're calculating the force of gravity, you don't have to put the negative in as long as you draw that in the right direction when you're doing your calculation of diagrams. So the force of gravity is good. We usually do Fg for that, just because there's different forces. So the G is for gravity, equals mass of the object times G. G is equal to 9.81 meters per second squared. So that's that constant. That's the acceleration due to gravity. Instead of using A, we write G, just because we know what that is. Weight depends on gravity, but it's not quite the same as mass. Now, this is one of those kind of confusing things that we don't really have to concern ourselves too much with. But if I was on the moon, gravity is different, right? That's why spacewalks happen the way that they do. So weight depends on gravity. So weight isn't the same as mass, even though in everyday language we would say my weight is 45 kilograms. Really, we mean our mass is 45 kilograms. It's a technical physics piece, but just if you're looking at that wording or you see that wording come up, the difference between weight and mass, that's something just to keep in mind. We won't spend much time on that just based on the amount of time you have for the concepts. But weight, when I talk about weight, what is the weight of an object? I'm always thinking about what is the force of gravity pulling it down. So what's the effect of gravity on the object? Last but not least, we have Newton's third law. So there were three laws. The first law says if an object has no force, then the motion's not changing or it's not moving, which not moving means the motion's not changing too, I suppose. His second law says that, okay, if the forces aren't balanced, so if there is an overall force, it will result in acceleration, and that acceleration will depend on the mass of the object. Newton's third law says for every action, there's an equal in magnitude, so equal in size, and an opposite in direction reaction force. So forces have reactions. If you have siblings, if you poke the bear enough, you will get a reaction out of them, right? If you pick on somebody enough, there's usually a reaction that results. That's Newton's third law in communications. But in physics, what it means is if we have two vehicles and they collide, the force the big truck puts on the little truck is equal to the force of the little truck on the big truck. The two objects impact with the same force on each. Okay? So the forces are equal. I'll put that in here. Which truck experiences the greater impact force? They're equal, according to Newton's third law. The reaction pair would be force of big truck on little truck, and vice and opposite. And I'm using just B and L for big and little because I don't have space. Okay, so those are your two forces. So which truck has the bigger acceleration? Well, let's just think for a second. Force equals mass times acceleration. The force on the two is equal, but their sizes are not equal. If the big truck has a big mass, will it change its motion easily? No, that's the law of inertia. All three of them kind of tie together, which means the big truck has a big mass, but it has a small acceleration. The little truck, on the other hand, has a small mass, but it's going to have a large acceleration, meaning it may accelerate to the point, have an acceleration to the point that when they impact, the big truck stops and the little truck gets bounced back, or the individual in the little truck gets thrown from the vehicle because of mass. Okay, so that's Newton's third law. Now, there's just a couple of definition forces that I just kind of want to take a quick run through. This is a good table to kind of keep on hand as you go through calculations. We're going to use most of these forces over the next couple days. So first of all, gravitational force, we talked about that. That's the force of attraction due to gravity. So on Earth, it's always going to be mass times 9.81, and that's what we will use. So that's gravitational force. It's just an example of Newton's second law. Friction force, we will calculate later. You don't need to have this formula yet. I've just kind of got them all grouped together so that if you want to print this page to have it handy, you can. It's a force that resists motion between two objects. I think we're quite familiar with that. But we'll look at that one separately, so we'll go into detail a bit today. Normal force is a balancing force due to an object on a surface. And we're going to talk about that force when we talk about friction force. But anytime there's a surface, a normal force is the opposite force for Newton's third law that would hold up. So my computer's sitting on my desk right now. It has mass, so it's pushing down on my desk. The desk is pushing up on the computer. I am currently sitting in a hydraulic office chair. My mass is pushing down on that chair, and the hydraulics on the chair better have a force great enough to apply a normal force to keep me up so that I don't accelerate downward to the floor and have an embarrassing episode. Okay, so that's normal force. And we'll look at that a little bit more in our future lessons. Applied force is any force that's put on an object. It could be anything. It could be from an engine. It could be from a push. It could be from a pull. So we'll see the word applied force. And that just means that a force somebody is putting on an object, and it's not one of the other common ones. And then net force is just the sum of all the forces, and net force can be found by adding all the forces up or by taking mass and multiplying by acceleration. And we'll use those two in combination like we already have. Now, there is a worksheet for you to do that deals with drawing a free body diagram. So a free body diagram allows you to show the forces on an object, and I'll give you the solutions for that. I'll give you a couple examples here. A box is pushed across a rough floor at a constant velocity. So if there's a rough floor, there's friction slowing this box down. So this is kind of a non-numbers thing, but it's moving at a constant velocity. Remember from Newton's first law that this means balanced forces. So the forces are balanced. So that means the force of my push, we've learned force of push is force applied, is equal to the force of friction that wants to slow it down. So that's how you draw a free body diagram. You just draw the forces. You could draw two other forces if you want. You could say there's the force of gravity pulling it down up to the floor, but there's also the floor pushing up. And when the floor pushes up, we call that normal force. Okay. A crate is being hoisted into the air by a crane at a constant velocity. Constant velocity means they're balanced. What forces are there? Well, there's no left or right forces if something's being lifted into the air, but if it's being lifted up, there's a rope that's pulling it up, and we call that tension. It's a type, just another name for the force. So tension pulls up, and it's balanced by gravity pulling down. So that's as simple as drawing a free body diagram, just kind of sketching. And I've got a couple other questions that happen. So you'll have a page where you have a few of these to draw just for some practice. Now this one is a really good example. You have a few questions like this to look at. Using the free body diagram, calculate the net force on an object. And if there's any motion, tell me what the motion is. So for the very first one, friction and applied force are equal. They're balanced. Normal force and gravity is balanced. If the forces are balanced, the net force equals 0. What do we know about the motion? Well, if there's friction, the object is moving. Be static friction too. Usually you think of an object's moving, so it's at a constant velocity, or it stopped. Because there is static friction as well. And you could say, well, if it's static friction, it could be causing it not to move at all. You'll have those little questions that you can bring out later. What about situation B? What's going to be happening to this crate? Well, it's sitting on a floor, obviously, because we've got gravity down, but we have another force upwards. So the upward and downward force are balanced, but the friction force is not balanced by anything else. This would be like applying your brakes in a car. Brakes apply friction, but you're no longer giving gas to the engine. So the net force is going to be 5 newtons, and it's 5 newtons left. Or you could say a negative 5 newtons. What's happening? Well, this one, there's acceleration in the left direction. Now, I don't know if you remember this from the last lesson. And maybe it's something that because we just did that one lesson on it, maybe it wasn't very clear. But friction is always in the opposite direction of motion. So let's say if something's moving forwards, okay, something's moving forward and friction's pulling in the opposite direction. Instead of using the word acceleration, we would say it is decelerating. So technically, deceleration. It's going to be slowing down. And that should make sense to us because friction is always going to slow an object down. It's never going to cause it to speed up. But in physics, we do use the word acceleration for both speeding up and slowing down. Situation C, what do we know about that? Well, again, we're balanced. And if this is a gravity normal force situation, there is no motion. The object is at rest. Sitting on a table probably. Situation D, we want to know, well, what's the net force? Well, there's 40 newtons up and 25 newtons down. So the net force is going to be 40 minus 25, which gives me 15 newtons up. If something's falling and air resistance is bigger than gravity, that's going to mean it's slowing down as it comes to the ground, like a parachute. Parachute is going to cause that effect. It allows an object to slow down as it hits the ground rather than the opposite, which would be speeding up as you go towards the ground. So this is another situation of slowing. We do have some acceleration. Does that make sense? Sometimes thinking about the motion can be a little bit tricky at the beginning, but you'll get a little practice with it. The last piece that we're going to do is we're going to just do some force calculations, and this will help you with one of the sheets that I'm going to give you for some practice. So we're going to use the diagrams to figure out the unknown force. So in the very first example, the net force equals 0, so all the forces are balanced. So we have balanced force, which must mean A balances the 50 newtons in the other direction. So it has to be 50, and B would have, oops, it's the arrows. We'll just go with the arrows being the direction rather than getting too little space in here. And B is going to be equal to 200 because it's balancing gravity. 200 up balances 200 down. Okay. Let's look at C. The net force, the overall force, is 900 up. What is the force that's pulling up? Well, we know if we add the forces together, the difference between the upward force and the downward force has to be equal to 900. So 900 is equal to C take away 200. You could rearrange that, but C is equal to 1100 newtons. And we're going to ignore this determine the mass of each object because we don't really need to worry about that here. We could, and that's just going to use F equals ma. We're going to leave that out for your particular calculation. And then this one. The net force is 60 newtons to the left. So overall, we have more force in the left direction. Got to do the other left. So 80 newtons is greater than D, and it's 60 newtons greater than D. So 60 is equal to 80 minus D. Well, how big does D have to be? Force D is going to have to be 20 newtons. Force E must be the balancing force to 300 newtons, meaning it's 300 newtons as well. And then the very last one. What do we know about this one? Well, the net force is 30 newtons, right? So G, if I subtract 20 from G, I'm going to get 30 newtons in the same direction as G. So 30 is equal to G minus 20. So G must be equal to 50 newtons. What about F and H? Well, F and H have to be equal. We don't know how big they are, but they have to be equal. Why? Because they're balanced. There's no motion, no net force in the up and down direction. All right. So that covers kind of the basic introduction to forces. I know that might have been a little bit of a lot for you. Hopefully the quiz will help you out a little bit. And then our next lesson, we're going to look at force with friction, and that should help reinforce some of the information, make it even a little easier for you to understand and get your head around.